Have you ever stopped and wondered what the odds really mean? We talk about chances and probabilities all the time, but what happens when the real world doesn't quite play by the rules of math? Well, today we're going to dive right into that, exploring the really fascinating difference between what should happen and what actually does.
So let's start with the absolute classic, the simplest chance experiment there is, just flipping a coin. We all have a gut feeling about this one, right? It's a 50-50 shot. But how often does reality actually line up perfectly with that 50-50 split? And that question right there gets us to the core idea for today. There's this huge difference between the clean, perfect world of theory and the often messy, kind of unpredictable world of reality. And in probability, we've got a name for both. Think of it like this. On one side, you've got theoretical probability. That's the perfect world. It's what the pure math says should happen. But on the other side, you've got experimental probability. That's the real world. It's what actually happens when you go out and do the thing. And honestly, that's where things get really interesting. So, sticking with our coin toss, in that perfect theoretical world, every single flip has a 1 in 2 or, a 50% chance of landing on heads. The math is simple, it's clean, it's totally straightforward. But then, reality hits. Let's say you actually do it. You flip a coin 10 times, and you get tails 7 of those times. Well, suddenly, your real-world result is 70% tails, not 50%. So what gives? Is the theory wrong? No, not at all. It just means that in small experiments, the results can look a little funky. So how do we measure the probability of what actually happened?
That's exactly where experimental probability comes in. And thankfully, it has its own really straightforward formula. But before we get to that, we need to make sure we're on the same page with a couple of key terms. First up is a trial. This is just a fancy word for one single go at the experiment. So, one coin flip, that's one trial. Flipping it 10 times, you got it. You've run 10 trials. Simple enough, right?
And next, we have the event. The event is just the specific thing you're looking for, the particular outcome you're counting. So in our little experiment, the event we cared about was the coin landing on tails.
Okay, so with those two words down, here it is, the formula. To find the experimental probability, you just take the number of times your specific event happened and you divide it by the total number of trials you ran. That's it. Let's break that down real quick. Step 1, you count your successful outcomes. For us, that was 7 tails. Step 2, count your total attempts. That was 10 flips. And step 3, just divide. 7 divided by 10 gives us an experimental probability of 0.7, or 70% for tails.
All right, now that we've got the formula down, let's put it into practice. Let's apply it to a few real-world scenarios to see how it works when the numbers aren't quite so neat and tidy.
So imagine a school cafeteria is tracking its lunch orders for the day. They sold 18 orders of adobo, 22 of bulalo, and 20 other meals. This chart gives us the raw data from their experiment, a single day of lunch service. So the total number of customers, or trials, is 18 plus 22 plus 20, which adds up to 60. So here's a question for you. Using only this data that we have right here, what's the experimental probability that the very next person to walk in is going to order bulalo? Take a second. Think about how you'd set up that formula.
So how'd you do? The event we're measuring is ordering bulalo, which happened 22 times. The total number of trials was 60 customers, so you just divide 22 by 60, which you can simplify down to 11 over 30. And that's it. That's our experimental probability.
Okay, you ready to level up a little? Let's try a trickier one. In this case, we know some of the outcomes, and we know the final probability for a different outcome. We have to work backward to figure out a missing piece of the puzzle. How would you even start with this one?
Well, the first step is always to set up the equation. Let's use the letter n to stand in for that unknown number of green spins. We know the probability of landing on green is 50%, or 0.5, and we know that probability is equal to n divided by the total number of spins, which is the 4 reds plus the 6 blues plus our mystery n.
And from there, believe it or not, it's just a bit of algebra to solve for n. We rewrite 50% as 0.5. Multiply both sides by that denominator 10 plus n, which gives us 10 plus n equals 2n. Subtract n from both sides and there's your answer, n equals 10. The spinner must have landed on green exactly 10 times.
So, we've looked at coins and cafeterias and spinners, but you might be thinking, okay, so what's the point? Why does any of this matter outside of a math problem? Well, let's get to the real takeaway here.
Because here's the crucial point. Experimental probability isn't just a game. It is the tool we use to make predictions based on real, actual, observed data. It's how we find patterns in what has already happened to make a really good guess about what might happen next.
Take this number, for example, 9 out of 10. Based on things that have happened in the past, this is the experimental probability of something happening. What do you think it could be?
This scenario really puts it all into perspective. You're on the basketball court, and you've been paying attention. Your friend's experimental probability of shooting the ball, just based on what you've seen, is a whopping 90%. That's not a theory. That's a pattern you've seen with your own 2 eyes.
And that leads us to the final thought. Armed with that knowledge, that data you collected just by watching, how does that change how you play defense? Do you guard him a little differently? Do you anticipate the shot instead of a pass? That right there is the entire power of experimental probability. It's using what has happened to predict and then react to what will probably happen next.